Hello. In the last video, we talked about basics of MPI. Also, we talked about different commands such as send and receive in MPI. Today, we continue with an example in which we write an MPI, a parallel program, to send and receive a character. So this may seem like a hello world, although we did a hello world program, but this is like a very basic MPI program. I would like to remind you that in this course, we are not going to make a deep dive into MPI. The goal is just to make you familiar with the basics of it, because MPI is too vast and we do not have time to cover the whole thing. We just want to introduce you the basics of it. Even in the assignment, you are just asked to run an existing MPI program and understand it, as opposed to writing it by yourself. All right, with that introduction, let us move on to this MPI example. So, as I said, this MPI program intends to send and receive a character. Let's see how to write such a program. So just to remind you, in the beginning we should have MPI.h, then normal C programming languages stuff like main, and then we generally have number of tasks, which just tells us the number of tasks if you need. That's generally needed. And rank, which is a much more important. Rank provides us with the process number. Rank is a critical part of MPI, using which processes can talk to each other. This is the process name, if you will, or the process address, or the process number, using which you can communicate between processes. And then some other variables. Note that these are just normal integer variables that we use for specific purposes. And then we have a couple of character variables, in message and out message, and the value of both is a capital X. The value doesn't matter, you can do whatever you want. Okay, in this example, we use MPI status. That just represent the status of a comment. And next thing we do is MPI init. I mentioned in the previous slide that MPI init is the first formal MPI command that initializes, and most importantly, it builds the network between the processes. So after this command, the processes can talk to each other. Without init, MPI init, we pretty much cannot do anything in MPI. Alright, so once we do the initialization, then we can use MPI com size, which is generally a useful command, gives us the number of tasks being created. So basically what it does, we use the communicator, and as a result of invoking this function, the variable num tasks, which is just a normal variable, if you remember from up here, it just is assigned with the number of active processes. And then more important than that, we have MPI com rank. You can just use this set of commands. It's very basic and very standard to MPI. So in this command, again, we use the communicator and assign a rank to each process that is running this program. So I would like to note you or remind you that in MPI, that's kind of the advantage of MPI. In MPI, we write just one program. So even though we may run the program on 100 different machines, or even thousands or 100,000s of machines, well, we generally do not do that big, at least in this course. However, in industry, in large scale simulations, they do this type of HPC programs. They are most of HPC programs are built by MPI. So so I would like to note to remind you that you just need to write one MPI program, and all processes, all processors that are part of that MPI program, they run that one program. They all run the same program. We have a single program. All of the processors run the same program. And then, the first one that reaches this line, it is assigned with rank 0. And that plays the role of master, a master part, or the coordinator across all other processes. Okay, so because all of them, all the contributors, all the MPI programs run the same program, each process running it gets a rank. For example, the first one gets 1, the second one gets 0, the third one gets 2, and so on and so forth. So the first one, as I said, plays the master, or we can say a coordinator. There's nothing specific about it. So the way we basically categorize who does what is based on that rank. So we say if the rank is 0, which means the process that has reached this rank command first and has been assigned the rank 0. So that process will run this part. The others will run this part of the code. So you can see else if rank is equal 1. Here, because our MPI program has just 2 processes, so we have rank 0 and rank 1. Often we have more than 2 processes. Therefore here in other programs you just see else, which means else rank whatever it is. It doesn't matter. You can divide the processes based on different metrics. For example, odd processes, or processes with odd rank, or processes with even rank. So depending to the logic of your program. And again, the logic of a parallel program, that's by itself a big topic. Basically, how to design an algorithm how to design parallel algorithms, which means using MPI pretty much. All right. So the first program reaches this part. See, because its rank is 0, this if command holds, and then it enters this block. So what it is going to do is sending a message to process number 1. So as you can see, it assigns dest, which is just a normal variable up here. It just makes it 1, assigned it 1. This is just normal C operation. And then it uses MPI-C for sending the message. So out message, if you remember, we just made it X up here, if you remember. And then 1, I guess this was the size of it. And then MPI character, as I said, we should mention the type of the data being exchanged. And then the destination machine. So the destination machine, somewhere we appointed to be 1. So if you look up here, you can see that, we assigned it here to be 1. So it says that we are going to talk to machine number 1. And then the tag, the tag doesn't do anything here. In many MPI programs, it doesn't do anything. And but in some cases it is useful. And then we have MPI convert, which is just a communicator. So the core of this message is just sending a message to another MPI program or MPI process, which is whose rank is 1. All right. So once the send is done, this is a blocking send. This is a normal send operation. Then we do the printf, which basically means that this send command is completed. In other words, this printf will be executed once this MPI send is complete, right? Because it's a blocking send. If it was non-blocking, it was moving on to the next command regardless of the result of the send. But here it's a blocking send. So then it says rank 0 sent, just acknowledges that the previous command is done, out message. And then it starts waiting in the next step. It starts waiting to receive a message from another MPI process. So we use MPI receive, and then in message, whenever we get the message, it will be stored in message. Size 1, we are expecting to receive a character from source. What is source? It's just a variable with value 1. And the tag, as I said, is we just had put it 1. The value doesn't matter here. And then MPI work, which is the communicator, and the status of whether or not the transfer has been done to receive operation, the content has been received or not. All right. For other processes, in this case, we just have one process, because here we have just two processes that talk to each other, exchange characters between each other. So if it's process number 1, then it has to first expect a message, expect to receive a message from process number 0. So we make the source 0, and we do MPI receive in message from size 1, type character from source 0, as you remember here. And then the rest of the things you are familiar with. And once it receives the things and it prints the content of it, then it proceeds with a send command. So it sends a message, outgoing message, MPI character, to the other segment of the program, other MPI process. And eventually we do MPI finalize. All right. So once we do this, we can run the program, and we do MPI CC to compile that, and then we do MPI run with two processes on the output of the previous command, which is a.out. We assume that that's the object file of the previous command. And then you are good, and then you can see the results of the execution. Rank 0 sent X, rank 1 received X. All right. So after learning about that example of MPI program, now I want to talk a little bit about non-blocking communication. So we mentioned that the message passing between two MPI programs, basically send and receive commands, can be blocking, which means that the program proceeds to the next instruction once the send or receive is complete, or sometimes it's non-blocking, which means that, for example, if we have a non-blocking receive, so once that line of code executed, it proceeds to the next line, regardless of that receive operation is complete or not. So for that purpose, we have MPI I receive. So if you notice, there's an I here, and MPI I send. So these are non-blocking. So the format is pretty similar to the other MPI commands. You can see again we have buffer, the size, the data type, the source, tag, the communicator, and a request. What is this request? This is the new thing. So this request is the handler. Basically, assuming that you have done the receive, the non-blocking receive, I receive basically, and then you proceed to the next line and next line and next line. But at some point, you want to confirm if that message, if that receive is complete or not. So using that request, you can assure, or you can check the status of the operation, of the receive operation. So for example, we have a command called MPI test that later on in your code you can use it, and it receives request as an input, and there's a flag that is kind of the output of it, and it will be true if the operation is complete. All right. So for the status, it doesn't do much here. You can ignore it. So status is not used in many of the MPI commands. All right. So there are some other commands like MPI broadcast,